So after the introduction to physiology and basically how the nervous system communicates, it's time to introduce the eye and vision. And we're actually going to start, and we're going to do this every single time in this really bottom-up kind of discussion of starting with the stimulus out in the environment. So in this case, the properties of light. We're going to get to the how is this transduction. So we're going to introduce you to the mechanics of, in this case, the eye, and then we're going to get to the properties of the photoreceptors, those actual sensory neurons that are doing that transduction. There are two ways to conceptualize light, to think about how this electromagnetic energy is moving through the world. In a wave, so when we talk about it as moving through the world, it's occurring in these different waves with different wavelengths, but those waves are made up of a stream of photons. And for understanding how we see the electromagnetic spectrum, we need to talk about both of these pieces and parts, because the photoreceptors are actually going to absorb a photon of light in order to fire. Experience of light is influenced by those waves, by those waveforms. So if we look at the electromagnetic spectrum, I have it going from gamma rays and X-rays and ultraviolet rays in those really shorter wavelengths. So if we look from peak to peak on the waveform, which is trying to show you up there in the top right, we have those really short wavelengths. As we get into about, they estimate 360 to about 700 nanometers. So a nanometer is a billionth of a meter. We're still unfathomably small here in our wavelengths. As we get into those wavelengths, that is the visible part for humans of the electromagnetic spectrum, where down towards 300 nanometers, we're at violet. If I go the other direction, it's a lot easier because I can do the Roy G. Biv in the way that I'm used to doing. So if we start up at 700 nanometers, we start at red. And then as we get shorter and shorter, we go to orange and yellow. At about 500 nanometers, about is green. And then we go to the Biv, blue, indigo, violet. For breaking up our white light with a prism, this is the part of the electromagnetic spectrum that we see. And we can see that it's made up of those components of those different wavelengths. We can go longer though. We can get into longer wavelengths as we get into infrared, radar, FM, TV, AM, and AC circuits. And you can imagine, so if we could see all of that electromagnetic spectrum, our worlds would be overwhelmingly noisy, right? Because we'd be seeing radio waves and cell phone conversations and all of that. So we want to have this nice little sliver that we get to see, that is the beautiful colors that that we see. Some animals do see shorter wavelengths. So those ultraviolet rays, I usually say hummingbirds, some of the insects like bees, some fish. Some animals do see up in the infrared range. So snakes, when they're sticking out their tongue, are sensing infrared light, but also some fish sense infrared light. But we get our visible spectrum from about 300 nanometers to about 700. I'm kind of overestimating on both ends. I think it's going 320 to 680. We're taking that information in. That light information is coming through the eye before it's going to hit the photoreceptors. What this picture is showing is the eye, and then the magnified piece is, here I am at the back of the retina, which I've already really briefly introduced, but the back of the retina, we're going to go through all of the optics of the eye, through that neural mush to get to those photoreceptors. This is where they are doing the absorbing of light, giving us transduction, and then giving us the information about light. And so as we're going through the eye, we're going to start the outer part of the eye, which is the cornea. It is doing much of the focusing of the light. So the light gets bent or refracted by the cornea and lens. And what we want to do with the cornea and lens is to get that information, to focus that image on the retina, particularly on the foveal retina. That's what the optics of the eye are made to do. And while the cornea is doing the most of the focusing, sometimes this estimate is up at 80–85%, the lens, it can do some accommodation. So it's the one that changes its shape in order to help focus that image on the retina. We're taking that information in through the cornea. It's going through the pupil, which is that hole in the iris that lets the light in. The iris, the muscles that constrict or dilate the pupil. To depend for this class, depending on the light levels, we're not going to talk about the autonomic nervous system, but just depending on light levels, I'm going to have a larger pupil when I am in dimmer light so that I can let in more of that light. The iris controlling the pupil, that is what we usually talk about when we're talking about someone's eyes, because that's the colored part of the eye. The lens, so again, it's doing the accommodating, so it's changing shape to allow for the focus of that image on the retina. And part of how it's doing this is through, well, how it's doing this is through the ciliary muscles, those muscles that are controlling the shape of the lens. To continue with a couple of concepts that for me you don't need to know, but it would be weird to skip them. So the aqueous humor, which is the fluid that is between the cornea and the lens, it's really removing waste, supplying oxygen and nutrients. We can keep our humors healthy by eating a healthy diet. The vitreous humor behind that, so if you poke your eye, don't poke your eye, but if you if you poke your eye a little bit, if you're out at the eyelid, you just poke a little bit. It's gel-like, it's kind of gushy, if you will. That is the vitreous humor that's filling the eye. It's behind the lens, and this is why we get those floaters that you see sometimes that you can't quite catch in your foveal vision, and you'll kind of chase it around. Those little floaters are pieces of vitreous humor, and it's absolutely normal. We all have them. Some of us notice them more than other people. Again, so the optics of the eye, that cornea and lens, are bending the light and refracting the light in such a way that we're focusing the image on the retina, and that's where the vision actually occurs, right? The transduction, because it is the rods and the cones, those photoreceptors that are allowing for transduction. And I've mentioned now the fovea a couple of times. The fovea, my foveal vision is where I'm pointing my eyes so that I can get that acuity. It is tightly packed with cones. And the other thing to address here, and I usually do a demo with this, so I'm hoping you all are watching and doing your demos, but is to find our blind spot. We do have a blind spot in each eye. If you close one eye, you'll notice that you don't notice the blind spot. Something has to be just in that blind spot, because what your brain does is it's going to fill in the information with what makes the most sense. Here at the blind spot, we have it because blood vessels need to come into the eye, the optic nerve needs to go out and leave the eye and take that information to the brain, and at that point where those axons are leaving the eye and the blood vessels are coming in, there are no photoreceptors in that space, and again, on each eye. Of all of these optics or mechanics of the eye is to focus that light on the foveal retina. We do see this accommodation, those changes in the shape of the lens to adjust that focus. And so if you want to do this demo, I'm going to suggest strongly that as you're listening to these, that you're doing these demos, because I cannot figure out ways to make this I'm going to try and figure out animations at some point. But I don't have a lot of animations. I know that it's a little bit dull, and so these demos not only help to break it up a little bit and help you get involved, but they really do help to apply and think about the information. So if you have a pen or pencil, hold it up in front of your face. If you don't, you can hold up a finger or whatever. So you're holding up something in front of your face. we're going to do this demo of, we're going to look far off. So look off into the distance. I can look outside at a tree, and you can see that that tree, or whatever you're looking at in the distance, is in focus. And then if you kind of bring your attention to your finger without looking at it, so you're still looking at the tree and focusing on that, you'll notice that your finger or the pen or pencil, it's kind of blurry, and there's this double vision, right? Because your eyes are working together, and they're working together to put the tree as what's in focus and what is like more singular. So what's happening right now is your lens, as you're looking far away, is flattening out so that you're not bending that light as much. That light is coming in more in parallel, and you don't need to bend the light as much as you look at something close up. So now change your focus to your finger, and what you'll notice is I can't find the tree anymore because there are too many trees, right? It's off in the periphery, and I've lost that acuity because that's off in the periphery, and my foveal vision is giving me acuity. But what you'll also notice is, so that's blurry, and if you have something out there, you might actually notice there's some double vision. What you're focusing on is your finger, and as you're focusing on your finger, your lens is getting fatter and fatter. It's getting, because now, if you think of how camera lenses work, I'm going to get fatter in order to bend that light more. That light is coming in at an angle, at an obtuse angle, and you need to bend it more to get it focused on the foveal retina. This is my slide to make sure there are not questions and to say things over again that I feel like need to be said. What I want you to do on these slides is to pause, take notes, write down questions, because I'm here. I'm here for questions, and you probably have them. And so you want to be aware whether or not you have those. But I will quickly walk back through some of that with this picture being bigger, that the optics of the eye, so I'm looking at a cup out in the environment, the optics of the eye are such that the lens and cornea are bending that light. And actually what you can see, because of the optics of the eye, that image, when it hits those photoreceptors and it becomes the proximal stimulus, it has been transformed. What you're seeing on the back of the eye there is an upside down cup. And if there were more sort of information around that cup, that information would look really kind of smaller and more blurry because, again, because of we're looking at the cup, and so it's on the foveal retina. Then they magnify out part of the retina, and you can see that that light is not just going through the cornea, the aqueous humor, the lens, the vitreous humor, but it's going through these neurons at the back of the eye, the retinal ganglion cells, those perpendicularly communicating cells, the bipolar cells, and then it's hitting the outer discs of those photoreceptors that are back against the back of the eye, hitting that what's called the pigment epithelium. And I'm going to come back to the pigment epithelium relatively briefly later. Write down questions. There are a number of clinical issues that occur here at the optics of the eye, and particularly with the lens and cornea, or it can be the length of the eyeball itself, but the lens and the cornea are part of what's really important for these clinical issues. Myopia is a relatively common, it's quite common, especially in developed nations. So myopia is another word for nearsightedness. More than 70 million Americans have some form of myopia. And so what this means is I can see when it's near and that light is coming in at an angle, but when that light is coming in parallel, as I get farther away, I have some point there where it's too much in parallel, and so I'm bending the light too much, and it's getting focused in front of the retina. And so we're going to give some kind of concave lens to bend that light out into an angle again so that it gets focused on the retina. Another way to do this, a concave lens would be like the way my glasses are made, but another way to do this is a LASIK surgery where they go in and they My understanding is they usually shave off some of the cornea because it's bending light too much, and so they just take some of that bending power, basically, away. When I say usually, so refractive myopia, I've been talking about refracting or bending the light. So that's when there's something going on with the cornea or lens. Again, usually the cornea really is doing too much bending since the lens is doing this accommodating. But there's also axial myopia, which is the length of the eyeball is too long, and so, or longer than quote normal. And so the lens and cornea are still bending the light too much to get it focused on the retina, but it's because the eyeball is long. Another clinical issue is hyperopia or farsightedness, where now we're not bending that light enough when it's coming in at an angle, and so it's getting focused there behind the retina. This can again be fixed with glasses and is somewhat uncommon, especially when we are younger. But if I go ahead into presbyopia, which I now resent, both of those things, which because it means old sight. So as we have older, as our vision gets older, getting that lens, or yeah, getting the lens to be fat the way we need it to be, it becomes a little crystalline. It becomes a little bit harder to do, and the ciliary muscles are weakening, and so we are going to have presbyopia as we age. And there's a line at the bottom that's showing it's going to get farther and farther away as I get older and older. And for some people, and this is very, it's going to happen. It's genetic about exactly when it happens. So it can happen as early as 39 years old. It's probably going to happen before the age of 49 years old, where you're probably going to want to get what they call readers, right, to just magnify things that are now close up. Because again, this farsightedness, because it's a farsightedness, I can see okay far away, but it's when things get close that I need to be able to bend that light more, and I can't. I'm going to end this particular slideshow here and start the next slideshow at this same place to repeat and put us where we are. So the optics, those mechanics of the eye, the purpose of all of those is, again, to focus that image on the retina, particularly the foveal retina, where we are pointing our eyes so that we can get that very acute, well-resolved information. So we're getting that information back to the photoreceptors, the rods and the cones. They're doing the transduction, and those two more overarching kinds of photoreceptors, the rods and the cones, they have differences between them that really shape our visual world. Those differences include difference in physical appearance, a difference in the distribution across the retina, as we've talked about the fovea a few times, again, where we're pointing our eyes, it is tightly packed with cones, giving us that really good acute information. The wiring to the brain, those circuits that we looked at, give us differences in acuity versus sensitivity to dim light. There's a trade-off there. And then we'll look at some clinical issues, which between the wiring and the clinical issues, the functional significance piece is going to fall out in a way that makes sense. You're going to say, okay, this was all things, this makes sense compared to what we've talked about and what we've seen with those clinical issues and with the wiring.